Hi, this is Chuck Benedict, mentor for Team 997 Spartan Robotics, back with another video. This is a follow-up video in response to the one that I did called the Untestable Command Robot, and I linked that video to a thread that I started on Chief Delphi entitled Never, Never, Never Use the Command Robot. I knew when I put it out there that it was going to create kind of a storm of controversy. Didn't really do it to get clicks. I really did it to call attention to the fact that I truly believe that the command robot template that produces a sample project for you from VS Code produces code that is untestable. And I think that is unacceptable, frankly. I'll recount a story. I play guitar. I do it modestly well, enough for my own satisfaction. But when I started learning, I learned on my own, picked it up, and I started playing and practicing or whatever. And I got to a certain point, and I wasn't getting any better, and it was frustrating. So I just kind of stopped because, there is anytime you learn something new, there's like this threshold that you have to get over before you kind of get any better. And I kind of got to that threshold, and I just got bored or frustrated and said, enough's enough. And I, then went to take private lessons, which were frustrating too, because the teacher was teaching me stuff that I had never done or knew or had learned before. And for a time, I actually got worse. And it wasn't until, I started practicing correctly where I found that I actually started improving again. And, I relate that story then to where we find ourselves with these templates that have been provided. They're good for beginning students to kind of get started and get something going. But the problem with them is that they perpetuate bad behavior. They perpetuate bad habits. And as you grow your robot program around those bad habits, your robot program is impossible to test. Now, there may be folks that debate me about the value of testing. That's a healthy debate to have. Maybe it is easier to use print lines to test your code. If you're a single member team, programming team, that may be so. You may have the luxury of having a RoboRio sitting right by you, by your workstation, and you just throw code on it and look at the console, and you can sort of tell what your code's doing. But if you're a team of 6 people, you don't have the luxury of having a RoboRio at every workstation. And I think it's so incredibly important for especially even beginning students to be able to run their code almost as quickly as they can write it. Because, let's be frank, if you're a new student and you've never coded before, you don't even know what to expect when you run your code. So I think even unit testing your code is so incredibly valuable. And so it's important to have the foundational template not impede you, let's just say it that way, not impede you from unit testing. You again may choose how much testing that you do, but if it impedes you from testing, well, then you can't do any at all. Okay, so I'm going to add this video to this thread because I said that I would, so it'll be here soon. What I wanted to do for this video is go through this template and I'm sorry to say it's going to be excruciating detail. It's going to make the video long. But again, this is my response to what I think is a solution to the practices that the old template perpetuates. So I want to explain myself pretty well. So the first thing that I'll call attention to is that the main robot program, the main robot program template, what I'm going to call the untestable command robot, kind of directs you to expose your subsystems publicly. Your subsystem the example one is declared as public, and it's also declared as static for no good reason that I can tell. And so what that causes is that it causes others to believe that it's okay to go reference that subsystem from the outside. And that's bad, because when you reference that subsystem from the outside, assuming that subsystem directly instantiates hardware, the class that references it is now So presumably that's a command. Well, that command now is not testable. So it's one of the reasons why to protect the state of your components like a treasure, don't expose them to the outside world, but only for very specific conditions that you control. So first rule, hide all that stuff, make them private. Again, there's no reason to make them static unless there's a good reason, and in this case, there is no good reason. And finally, I have labeled these final because we want to count on the fact that these things don't get changed out from under us. And there's reasons for doing that, and I'm going to talk about that reason a little bit later. But things that I don't expect that will change out from under me, I'm going to declare them final so that if somebody does later on, it actually doesn't prevent them. And if they want that to change, well then it's incumbent upon that person that's doing it to go make sure throughout the rest of the class that they don't break other behaviors. Next, so you'll notice that they're declared private and I don't instantiate them. So normally in the template program, there is not a default constructor that is provided on the robot class. Again, I think that's bad practice. You should be very deliberate about how classes are constructed and built. And if you just leave that up here, outside a constructor block, I don't know, I just kind of view that as sort of helter-skelter. Create a constructor, stick all of your instantiation of dependencies inside the constructor. And that way, again, you're being very deliberate. Now, what I have to note about this class still is that if you go into a test and you instantiate the robot class right now, that test is going to fail because this instantiation is going to try to call real hardware, and of course on the bench you don't have real hardware. So this robot class right now is still not testable, and in order to make it testable, you're going to have another constructor here where you pass in external dependencies, just like you do in classes that I'm about to show you. But it's a little more complicated. I've actually run up the food chain of the robot class to its superclasses to kind of see how WPI wires all the stuff together. And again, they don't do it in ways that make this testable. I think there are ways, and I'm going to continue to work on this to where it is testable. But frankly, it's not having this class testable is not quite as important, in my opinion, as having your subsystems and your commands and command groups testable, because that's really where all your robot activity is going on anyway. So moving on, one of the other things that I changed up, there was this class called OI in the old template, and that's where you wired up your operator interface. So you hooked up your commands to your joysticks or the buttons or whatnot. And I always looked on that class with a curiosity. Why is it there sitting off by itself? Why does it not have a constructor? Why is code just sort of scattered out through the class code block? It's just always been kind of a, why is it there? I think it's there because it was a centralized place to put all your operator interface stuff so that it's not scattered out all amongst your robot program, which kind of makes sense to me. But why make a separate class? It's actually a feature of your robot in the first place. So why not just add a method and do all the wiring up in your method, and then in your robot init you just call the method. So this would be the place now where your OI sits. Seems simple enough to me. So I factored the OI out. I don't think it makes sense. I did it that way. Now the rest of the main robot program class, I didn't change. I left it alone. So there was an example of how to use the chooser by wiring up the default example command that was in the template. I left that alone. Fine, whatever. I did wire up one button to actually flash the LED, and I'm not sure that I mentioned it actually. This template was changed to be a hello world template, if you will. And in the hello world for hardware, you usually make an LED flash. So that's what this does. When you put it in teleop and you hit the A button on your joystick, the LED flashes. And at the end of the video, I'll show that it does indeed work. So some people are going to say, well, it's not really a template. It's more like an example. Yeah, it is. If I do a template without showing an example, some kind of example, I think that that some people are going to slip back into old practices because that's what they're used to doing. So it's really kind of necessary to show an example of using good practices. You can rip the stuff out. It's easy to rip stuff out. Okay, so nothing else in this class changed, so I'm not really going to spend any more time going over it. Now, let's go look at our subsystem first. So here's I took the example subsystem and I put hello world functionality into it. So in our hello world subsystem, we have simply an LED. We have a constructor. The constructor takes a reference to the LED. Notice we do not instantiate the LED inside our constructor. We always now pass external dependencies into our created classes so that we have the ability to test those classes by mocking those dependencies out or mocking them up in a way that we see fit as we create our test. That sort of gets me back to or gets me to this notion that I want to introduce called an invariant. So an invariant is an idea that holds true no matter what happens. And in this case, it's something that I'm going to state for my class that holds true for my class regardless of whatever else happens in the outside world. In the old template, in the untestable command robot template, you can create classes that you are unable to instantiate. Well, when you do that, you can't test them. So I want to declare an invariant that you always can instantiate your classes. And so the way that you ensure that you do that is that external dependencies get passed into your class. So that's now something that is always true. Your classes are now always instantiatable. That means you can always test them. So that's an invariant. I've also declared another invariant. And again, when I say declare, that's not like a Java concept. I'm just like stating this idea. I have this invariant which says that our class always assumes that a valid reference to our hardware component always exists. So in this case, our LED, we will always have an LED internal to our class that always contains a valid reference, such that when you make a call to it, you should not get a null reference pointer exception back. And the way that that's done is our constructor does an explicit check on the LED that you pass into it to see that it's not null. And if it is, it throws an exception and prevents you from it prevents instantiation from occurring. Of course, it doesn't prevent it from always occurring. You got to pass the right stuff in, but if you pass the right stuff in, then instantiation is allowed. Furthermore, what happens if a developer creates a default constructor and they don't instantiate, or they don't instantiate the LED? They don't create an LED for you. They maybe count on some future method in here doing it. Well, that breaks the invariant, because again, you always want to be able to instantiate this class where a valid LED always exists. So I went on ahead and did something that maybe you probably wouldn't normally do, but it explicitly throws an exception if you attempt to create a parameterless constructor. And so what you're doing is you're telling, again, if you're working in a team, 6 people, you're simultaneously changing code. You as the creator of this class, well, you know that you don't want a default constructor because you always want to pass in your dependencies. Well, developer B may come into this and say, well, that's dumb. I want a default constructor. So they put one in, but they don't know about your invariant that says that you should always be able to instantiate your class. So they've now broken your invariant, but they didn't realize it. Well, by putting this in here, that tells developer B, hey, I'm intentionally making this something that you don't want to do, so don't do it. Again, think of it like defensive driving. You're defensively programming. You're being helpful to your other team members to say, hey, I've thought of this. This is something that I don't want to have happen, so don't undo what I did. Next, so now you're passing in your dependency, your hardware dependency from the outside, and again, you're declaring it private. Up here, this hardware, it's private. I can't reach in from the outside and get and grab onto it. Also, it's final, and let's talk about finality for a bit. Let's say you didn't declare this final, and let's say you had a way after you instantiate the subsystem to go change the reference to your digital output. So, at one point in time, your digital output is pointing to point 0 or port 0, and let's say later you change the reference to point to port 1. Well, if at the time of that changing, that state of that digital output is at state number 1, you've now abandoned, by changing the port, you've now abandoned the state or the access that you have to that old port to set that state however you might actually want to set it. So, unless your class counts on the fact that these references can change out from under itself, you should declare them as final. And that actually then alleviates you as the class author from having to account for the fact that, that stuff can get changed out from under you. So that's why, again, be deliberate. Label these things according to how you actually expect them to be used. I expect this to be done finally, which means once I instantiate it in the constructor, I don't ever expect it to change throughout the life of the instance of my class. All right. So because it's private, we still need, of course, our subsystem to expose interesting things to the outside world as the user of the class. So, we need to be able to perform things against our subsystem. So we need to be able to turn on the LED. We need to be able to turn off the LED. And it's useful to be able to toggle it so that I don't have to create an accessor method to actually get the state. It actually might be useful to get the state. For this example, I didn't need to, so I didn't create one. Finally, the init default command, the old template, it has this comment in here. Oh, you might want to call the set default command method and pass in a new reference to a command. Well, again, don't do this because you don't want to couple your subsystem to commands. Bad. Don't do that. I mean, if you want to do that, you must pass a reference to the command that you want to be the default in the constructor, and then down here in emit default command, you would call set default, but you'd call it against the command that was passed into the constructor. And then again, that way it maintains loose coupling, makes things testable. That's, you always want to enable your classes to be testable. All right, so this is our very simple command, our very simple subsystem, which operates on an LED. Now let's go look at the command that does the operating on that LED. This again was taken from the example command that was in the untestable template. Of course, that command actually didn't do anything. So it's kind of bad that it didn't do anything because, again, it leaves you to your own devices to continue with the bad behavior that's been demonstrated in projects past. So I've put some sample code in here to execute our hello world to execute our hello world program. I call this command say hello because it flashes the LED. That's what I'm calling saying hello. So it takes a final reference to the hello world subsystem, which we just talked about. Declares a working variable. We'll talk about that in a minute. Now, here's our constructor. Again, we don't hardwire the creation of our Hello World subsystem inside this class. We simply take a reference to it. And, this is the code that actually sat in the old untestable command robot. Don't do that. And now we've actually made this impossible because we have made the subsystem that's instantiated in the robot class private. So this actually doesn't work anymore. What we want to do is we want to require the subsystem that our command uses based upon what we've passed in. And again, the requires is important. It's important that you tell your commands what subsystems this command uses, because that's how the WPI scheduler knows how to preempt one command that's running that uses a subsystem with another command that wants to run that uses the same subsystem. So this line of code is very, very important, but don't make global references to things that require the robot to be running, because when you do that, you can't test it. We set a reference then to our subsystem because we're going to use it later. Got an initialize method that sets a working variable. That's pretty obvious. So now our execute method. So what's our execute method going to do for hello world, for saying hello? It's going to flash the LED. It's that simple. I could have used PWM to do it. It's less interesting for the purposes of this test, so I did it manually to kind of show how to do it. I don't use thread sleep. Never use thread sleep in an execute method for a command because it ties up your thread that prevents then other commands from executing in a timely fashion. So what I do is I simply look at the current nano time, and I see from execute call to execute call whether enough time has elapsed to cause my LED to toggle its state. The command, in this case, this command never finishes. At least it doesn't know whether it needs to finish, so I always return false. Your other commands, of course, may need to finish, so obviously you'd set them true under those conditions. End will actually never get called, at least because is finished is never going to throw true. However, at the end, we do want to set our hardware, or really our subsystem, to a known state. So in this case, I am telling my subsystem, hey, just make sure the LED is turned off when we're done. Because the normal use case for this command is to always be interrupted, because again, we're gonna stick this probably behind a button when button is pressed, and so when you release the button, what the scheduler is going to do is it's actually going to cancel the running command. And when that running command gets canceled, interrupted is the actual method that's going to get called on this command. So I just simply make a call to end, which of course turns the LED off. Okay, so in effect, that's all that happens here. I have a subsystem that has an LED in it. I have a command that flashes the LED. So how do we go about testing this without a robot? The template, the default template, the untestable command template, it doesn't have any means for automated testing. There's no test directory. Therefore, there's no tests. So any good testable command template would have a test directory, and it would have, a test directory hierarchy associated with it. For places for you to put your tests. So I have, and I can say with a pretty high degree of confidence that I actually have what's called 100% test coverage. Now, test coverage can be defined loosely or very strictly. You can say that test coverage is defined by the fact that all my methods, I at least have a test that actually calls into all my methods. I can say for sure that I have that. So I have 100% test coverage based on that criteria. The real definition of test coverage is that all of the code is covered by a test, meaning branches to if statements, branches to exceptions, catch blocks, finally blocks, everything has a test that represents coverage for code inside all of those areas. Can't say for 100% certainty, and there are utilities that you can run to actually make that determination. I can't say with 100% certainty that I have all that, that much test coverage, but as we go through this, you're going to see I test the snot out of everything here. Again, as a demonstration of good practice. Your conditions may warrant much looser interpretation, but hey, at least if you get a look at what really thorough testing might look like, that might inspire you to do that kind of testing as well. Okay, so at its most basic level, let's go look at a subsystem test, a subsystem unit test. So again, subsystem unit test means we're trying to narrow down the subsystem, factoring out all the other external dependencies. I don't want a RoboRio. I don't want an actual digital output to actually work. I'm not testing whether that works. I trust that WPI has done its job and has actually developed a digital output piece of hardware that actually responds the way I expect. So I don't want to test if any of that stuff works. I just want to test whether the code that I wrote in my subsystem does what I expect it to do. So right out of the gate, actually, I've already declared several invariants. I've declared an invariant that means that I should be able to always instantiate my subsystem. So we should test for that. So I have an explicit test. It should instantiate given an LED. So here's my subsystem. I mock it out, and I'm not going to talk about mocking here much. I have other videos that talk about Mockito and the purpose of mocking. Go watch those videos. Go read about Mockito. I'm going to assume that you kind of know something about mocking. So I mock out my digital output class and just simply pass it into my subsystem. And I just expect this class to this method, I just expect it to run. I also explicitly declare, so in this test decorator, you can pass in a parameter to the decorator that says, I expect when this method executes that there shouldn't be anything left on the stack, meaning that there shouldn't be an exception. And so that's what this test.none.class means, that there should be nothing on the stack when this method executes. So that means that when I call I instantiate my subsystem, it should just simply work, and nothing more remains on the stack. So this is a useful decorator to put that, again, is very explicitly telling the test, and it's telling the a reader here that you don't expect an exception to occur here. Next, remember on my my command, actually let's go back there. Sorry, not my command, my subsystem. Let's go back to our subsystem. In my constructor, I made a call or I made a check to my hardware to make sure that it wasn't null. Well, again, we should exercise that. Let's exercise that in a test. So here's a test. It should not instantiate with a null LED. So if you try to fool me with nothingness, I should throw an exception, and I'm going to test that I get an exception. So again, I do the same test as I did up here, but instead I pass null. And now I should expect an illegal argument exception to get left on the stack. So I'm going to catch that so that this test will actually pass. Because if you leave that on the stack, the test is actually going to fail. Next. Remember, we also created another constructor. We deliberately created a parameterless constructor. So hey, let's test that if you call that, you actually get this. So again, I did that here. I call the parameterless constructor, and as expected up here, I check to make sure I get that illegal access error. All right, next, a more interesting test. It should turn on the LED. So remember, I have a method over here, turn on LED. I call on the hardware, I call set with a true. So in my test, my unit test, I mock my hardware, I pass it into my subsystem. This is now the class under test. I call the method turn on LED because that's, this is what I'm trying to test, that this method actually does what I expect. Then I call an assertion where I verify on the mocked hardware whether or not the set function was called with true and whether or not it was called one time. That's what this does right here. So again, I'm not testing the actual hardware to see whether or not voltage is getting applied properly and all of that. I'm or whether the FPGA bits were twiddled properly to assert voltage on the signal line. I'm not going all down to that level. I don't, for the purposes of the unit test, I don't care whether that's happening. All I care about is whether me as a developer called the right thing on the class to actually cause it to set the state to true. So likewise, I do the same thing for the turn off function. Not going to really cover that. Okay, so this is a little bit more of an interesting test. This is testing the toggle. So remember, I have a toggle function over here, toggle LED, where I get the existing state of the hardware, and then I negate it and then set it to that negation. So back over here, I have a test, should toggle the LED. So this requires me setting state instead of just mocking and nothing happens on the mock. I actually need to mock it, but then I need to mock the get method call on the hardware so that it actually has some known state in it, because my subsystem is actually going to count on the fact that state is there so that it can negate that state and then actually set it to that negation. So I need a way to test that. So Mockito has this ability to cause, when a method gets called on your mock, you can cause a return value, a predictable known return value, to get returned. And so that's what's happening here. The first time that I call get on my mock, I'm going to cause Mockito to return back to the caller a false Boolean. You can also not very nicely chain your state together such that when you make a subsequent call to get, you can return something different. Well, again, for completeness, I'm calling both. I'm calling both states that this can be. I'm calling false and then I'm calling true. So that causes me to have two acts and two assertions in one test. A good practice says you probably really shouldn't do that, because again, it causes two tests to be run in one, and that causes the runner to have to do a little digging. Like if one of these fails and one of them doesn't, it causes the debugger to have to come in here and go, there's two assertions, which one of these is failing? It makes, you probably should label this, it should toggle the LED to false when it's true, and then another test of the opposite, because again, you want to be very deliberate and meaningful about what your test is doing. But I wanted to demonstrate the fact that you can chain these things together, because that really becomes important when you're doing more sophisticated testing, like say you're testing PID and you're counting on from call to call, things changing to affect your results. Well, you have the ability to very easily do that with these kinds of techniques. So I wanted to demonstrate that here. So I have I make a call to toggle. Because this first call should return false, well, I know that I should be setting it. I should be calling the set function on the hardware to true. So that's what this tests. I call toggle again. Again, this second return is going to turn true, so I know I should be calling false. Finally, the last bit that we didn't test, I kind of blew past it, but back. Oh, sorry. I thought this was something else. Okay, so this final test, it sort of kind of doesn't go with the command, but it kind of does. and this is really, it's kind of silly, but I've actually seen this happen in competition. So, you can use tests as kind of a workflow step, meaning that, what happens. So I did maintain the robot map as a useful feature. I do use these things as statics. Statics aren't inherently evil, but you should only use them when, there's a deliberate reason to use them. And there is a deliberate reason here to use them. These in your robot map, it's a good idea to just put all of these magic numbers, these constants, in one central location. It's good practice. And my LED is sitting on port 0. Okay, that's fine. But what happens if somebody just comes in here and changes this to something else? Well, presumably you've made communication to your electrical subteam that of what this robot map says. Your subteam may or may not have access to robot map. They may or may not review the contents of it regularly. Things happen. Perfect communication does not happen. So, you could use testing, unit testing, as a workflow mechanism to cause the person that makes a change to robot map to know that, hey, it's important that you go tell your electrical subteam that this has changed. So why not put a simple little test in here? Tell electrical that LED port has changed and then update this test. So if you change robot map and you run your test, this test right here is going to fail. It's not going to let you build your code until you come in here, until you get the nag, you acknowledge the nag, and you change the contents of the test. You could actually get really fancy. You could put some code in here that would actually send an email or send a text automatically to Slack or, your developers to, cause the actual automated workflow to do the notification. And in industry, that's what people do. You're having to work with others, and do you want to have to count on the fact that you've done the manual step? Well, if you've automated that workflow step in code, it's taken care of for you. So again, something to think about. Okay, let's look at the command test. All right, so again, unit testing our say hello command. So we don't really care what's happening to the subsystem that this command is acting on. We are testing the behavior of the command itself. So, let me back up. So if we're testing the behavior of the command, the behavior of a command is to be run under the context of a scheduler. And the scheduler, and I'm talking about the WPI scheduler, the normal behavior is for execute to get run periodically. I think it's every 20 milliseconds. So, in order to test the behavior of your command reasonably well, you've got to simulate the fact that there is this scheduler that is running your execute method every 20 milliseconds. Now, you could say, well, let's just pull in the WPI scheduler and just use it in our test. I actually think that's possible. I haven't tested the scheduler in that context to know whether it has external dependencies that would or wouldn't work in the context of a JUnit test. Probably it will work, and I am eventually going to test it. But it sort of breaks the notion of, in a unit test in particular, you really want tight control over all your dependencies. You want to know what those dependencies are doing so that, if somebody makes a change to those dependencies, it doesn't cause your test to break. So I decided to just create my own scheduler. I call it a helper. Under this directory right here, edu WPI, and I'm actually putting it under this path for a specific reason that I won't really talk about, but at this point, because I have to have some references to some of the WPI stuff. But I created a scheduler. It's called Scheduler Test Helper, and it's a very simple scheduler. A critic's going to look at this, and I apologize for not having comments. I will go in here and put some comments in before I check this in. A critic of this class is going to come, well, Chuck, it's too simple. It doesn't schedule multiple things, and it doesn't have a preemption mechanism, and. Yes, I know. It's very simple. It's intentionally simple. It just allows you to schedule one command and run that execute method and initialize the command and end the command appropriately so that we can unit test a command properly. So it's very simple. It doesn't do the full suite, but it does it does do the essentials of what a scheduler should do to a command to be able to exercise that command properly. I'm not really going to go into all of the nuances of what this does. There's some advanced stuff going on in here. It's not too hard, but it's not useful for the purpose of this video. Just know that for our command unit test, there is a before decorator and a before method that sets up our scheduler. It passes in 20 milliseconds as for the constructor to cause the scheduler to execute, to cause execute to run every 20 milliseconds. There is an after method that destroys the scheduler because the scheduler uses threads to run your command, and you have to clean that stuff up when you're done. So there's a destroy method on the scheduler to do the cleanup. And again, I'm going through testing. I'm going through the JUnit framework as if you know what before and after do. And if you don't, go read. I'm not going to take a lot of time to explain the stuff. Go read about JUnit so that you know what these options are available, these decorators are available to you for testing. Finally, so I want to test the behavior of my command, and the behavior of my command is to flash the LED every 200 milliseconds. And so what I want to validate is that on my subsystem that I'm calling the proper methods that indicate or illustrate that the LED is flashing every 200 milliseconds. So how do I do that? I mock up my subsystem because, again, I don't care what my subsystem does. I don't care what it calls under the covers. I just want to know that I'm calling the right things from my command on my subsystem. So my class under test is my say hello command. So here's where all the magic happens for this. On my scheduler, I want to run my command for a given duration. So in this case, I want to call it for 3 seconds. That's what the 3 here means. I want to call it for 3 seconds, and I want to wait for the scheduler to get done making that call. That's what this get function does. It's unfortunate in Java that when you make a call to something called a future, that calling get is actually what you have to call to await for that future to finish. It'd be better maybe if they called it await. Again, I really get kind of a stickler with the English language use of these methods because I really want it to be meaningful about what's going on. They call it get because with a future, you can actually get the result of what the future returns. And so you call get on the future. If I hover over for duration, you can see that for duration returns a future. So the get is getting the value. In this case, the value is question mark, which means null. It's getting when the future returns, null is going to get returned to you. Well, in this case, I'm getting a null for the running of the scheduler because the scheduler is done. Well, that's fine. The scheduler doesn't return me anything. I just want to wait for the scheduler to finish. So that's what the get is doing. Okay, so what I want to know ultimately then is how many times did toggle LED get called? So 200 milliseconds. I'm running for 3 seconds. So 5 executions every second. There's 3 seconds. Should be 15 times, right? Well, and 15 toggles, 15 flips back and forth of the LED against the subsystem, meaning I'm looking to see whether toggle LED was called on the subsystem. Because if you remember back on the subsystem, I used a timing mechanism. I'm measuring nanoseconds elapsed. Because there's other things that are going on my computer, it's not exactly deterministic how many nanoseconds are actually going to elapse. Sometimes you might get 14. Sometimes you might get 15. So I account for that by putting 2 different verifies in here. One verify checking that that my toggle is at least called 14 times, and one that is called at most 15 times. I think there's a way that you can specify a range in Mockito land. I did a little digging. It wasn't really obvious. I said, never mind. At least that's an exercise to the watcher if you want to go figure out what it is and leave me a comment. But this is how I know then on my unit test that my command is toggling my LED the right number of times based upon the timing code that I put into my command. Next unit test. You'll recall in my command, where is my command? Let me bring that up here. In my command, here we go. At the end, I turn the LED off. So we should check whether that happens. Unit test, command unit test. Here we go. So it turns off my LED when stopping. We want to check to make sure that happens. So here I run my command again. I run it for a shorter period of time because it doesn't really matter how long I run it. I just want to check that when it's done, my LED is in an off state. So here's my verify. I verify that on the mock, one time turn off LED was called. Now, in Mockito land, all this is doing is just detecting whether or not at any point that on this mock turn off LED was called. This doesn't actually check that it was called last. I think there's actually a way to do that. There's something called ordering in Mockito land where you can look at the order in which things were called and then sort of look at the last thing. Seems a little cumbersome to use. I think there's a way of going about it, but just realize that this test is actually not testing what you really, really want to test, which is the fact that this thing needs to get called last. Again, another exercise for the reader. Finally, remember I talked about the registration of subsystems that, to a command. It's a really important thing to do. So test for it. Why not? I mock my subsystem, pass the mock subsystem into my command, and I instantiate my command. And remember the registration, let me go back to the command. The registration is in the constructor. Here it is, requires, and here's my registration. So back to my unit test, it registers the correct subsystems. Why not? You should test for that. So here you go, assert true. Now, here's a little trickery. WPI nicely put a does require method on a command that allows you to test whether or not a command requires a subsystem. Problem is they declared it protected. So from this package, I can't go call into that protected method on my subsystem. So how do you fix that? How do you get around it? Well, you can do a little trickery. I've created this command helper. As long as you do it in the context of the package where the command exists, which is why this is in the edu hierarchy in my test directory. I just simply created a static, and again, static's not inherently evil, but a static works in this case. I create a static where I expose does require, and because I am in the package where command exists, I can actually make a call to does require now. So I can take in a command and I can take in a subsystem and I can call does require on that subsystem and return whether the subsystem appropriately knows, or whether the command actually knows about the subsystem. So that's how this little trickery works. So back to my unit test, I simply call my command helper and find out whether or not I appropriately include my subsystem into my command. All right, so pretty thorough unit test, right? Hey, I'm able to test whether my command does what I coded it to do. And I contend that you should be able to write any unit test on any command exercising any hardware. So, hey, feel free to challenge me on that notion, but I contend it's doable. Is it the most expedient use of your time? Yeah, I think it is, because I guarantee you, and I'm talking mentor to mentor now, you look around at your programmers and, aside from times where they may be screwing around, you're going to find time where they're not doing anything. You're going to ask them, what you doing? Nothing. Why? Because I'm waiting on fill in the blank. Ask them, how many tests have you written? Have you written any unit? Have you written any tests? Do you know there's a way that you can write tests? Do you know there's a way you can run your code? A lot of them are going to go, really? Huh, it'd be really nice if I could run my code. Explain to them, show them, hey, there's a way that you can exercise your code. Why don't you start writing some unit tests? Run your code. It's fun. So last thing I'm going to show you, integration test. Let's go look at an integration test. So the last test that we showed was unit testing a command. So we didn't care what happened to the subsystem under the covers of the subsystem. We just cared that we called the right stuff on the subsystem. So let's write a unit test that actually does, if we think about an onion, it goes in. Let's write a test that goes into the subsystem from the command and checks that we're twiddling the right bits on the hardware that live within the subsystem. So again, we need a scheduler because we're gonna exercise the command. So we wire up our scheduler again as before, and we have the same. Our test is named the same thing, but it's run in the context of an integration test. It's fine. You can name it the same because the name of the class gives you the context anyway. So if you look at it in the console, we're going to do that in a minute, you'll see that it's same test name but run under a different test. So this time though, what do we want to do? So we want to mock our hardware still. Again, we don't have real hardware, so we're going to mock the hardware. So we're going to mock our digital output. However, we're not going to mock our subsystem like we did in the unit test, the unit test for the command. This is an integration test for the command. So we're wanting to test the integration of our command to our subsystem. So we don't want to mock the subsystem up anymore. We actually want the subsystem to run. So we're going to instantiate the subsystem. We're going to pass the mock of our hardware into the subsystem. Then we're going to instantiate our command with our class under test, which in this case is a subsystem, because we're actually going to test whether the subsystem itself has the right that the hardware within it had the right stuff called on it. Again, we're going to run our scheduler. We're going to run it for 3 seconds. Now, what I'm testing for this time is whether or not the LED actually got flipped to one state or the other the appropriate number of times. Well, again, running every 200 milliseconds, running the execute every 200 milliseconds, so 5 times a second, I'm running for 3 seconds, so 15 times, and I have 2 different states it can be in. So it better at least be in one state or the other 7 times. So I'm verifying that the LED hardware, the mock of it, I probably should label this mock. Sorry, I will do that before I check it in. So our LED mock got set true called on it at least 7 times. So that's an integration test. Again, I don't care if the hardware actually works. I just care that what I'm doing to the hardware does what I expect it to do. All right, now this long-winded video, which is probably going on for hours. I don't know how long. It's be very bad if I actually didn't show it working. So let's watch it work. Run Gradle clean just to make sure everything is all cleaned up. I'm going to run, let's see, I have my RoboRio on. I'm looking at it. I've got it on. I'll show it in the camera in a minute. So I'm going to call it Gradle deploy. Actually, you know what? I'm going to turn my RoboRio off. Click, RoboRio is now off. I heard the beep. I don't know if you could hear the beep or not. No RoboRio is now running. This actually wouldn't be complete if I showed you these tests are actually not running on the RoboRio. So Gradle W, spell it right. Gradle W build. I don't know if do you guys like football? I spent yesterday what seemed like an eternity watching my beloved Aggies. Still got my Aggie shirt on. Play LSU. That's the big rivalry. You know, it was a really good game. I encourage you, if you love football, last 2.5 minutes. If you can rewatch it on, you know, ESPN replay or whatever, go watch it. Now, you think to yourself, "Oh, last 2.5 minutes, I'll go watch it." Whatever. You need to allow yourself a couple of hours. 7 overtimes, 7 OT periods. Most unbelievable football game I have ever watched. My Aggies won, so I loved it. If you're LSU, hey, you might not like it so much, but anyway, unbelievable football. So many weird calls. Officiating was done just perfectly, even with the weird calls. So much good play. It was an astounding game. Okay, anyway, that's my time filler. Here we go. Tests. Looky. I think I counted them. There's 12. 12 tests. They all passed. It's a beautiful thing. It's great. Look at that. I know my code works. I know it's going to run. You know, seriously, folks, this gives you, there's so much testing done here. This should give the author confident that the first time that I deploy this code, I know it's going to run. I know it's going to do what I expect it to do in here because I have tested the heck out of it. So, question is, did it? Well, let's deploy it. All right, I'm going to turn my RoboRio on. Actually, while I wait for all this stuff to work, I will not keep you in suspense anymore. Did it actually work the first time? No. I wired up my LED, wired up my my controller. Didn't work the first time. You know, I got to be honest, that disappoints me to no end. So, you know, I started thinking to myself, what's wrong? That little doubt starts creeping in. What did I do? I tested it. It should work. You know, what could I have So I start doubting myself, doubting my coding, doubting my tests and whatever. And that 10 minutes elapses and I'm looking at code and, you know, did I pick the wrong port and did I plug it into the wrong port? You know, all these things start swirling through your head. And then I look down at the RoboRio and I realize I wired positive on the LED to plus 5 volts. I didn't wire it to the signal line. Duh. Again, this goes to show you, you can't rely strictly on testing. You got to put the thing on the field. You got to test it. Well, you know, yes, obviously, you have to put it on the field. You have to see how it's going to work in real life. You know, you're validating your electrical team's ability to wire it up correctly. So, you know, obviously. Still disappoints me that I couldn't tell you guys right out of the gate it worked perfectly. Okay. So let's go run the driver station. All right, here's my driver station. I got code. I'll actually go over here to the little variables pane because this digital output, this sucker will flash too. But I have the LED on, so let's go look at the LED. Again, I'm gonna move the camera. I don't like doing it, but you know, you got to see the thing in action. Why not? You sat through it for this long. So here we go. I'm gonna move the camera. Hopefully this is pointing at the LED because I have my preview window. All right, I'm pushing the button. Here's my A button on my controller. Oops, wait, I got to put it in teleop. I got to enable teleop first. Hang on. Okay, now teleop's enabled. Pushing button. LED is flashing. There's my RoboRio. All right, I have proved it. So button's off, it's off. Button's on, it's on. Hooray, I have proven to you guys that you can code up stuff, test the heck out of it, deploy it, and have a high degree of certainty that your work is actually going to run on that thing. And you know, you have fun while you're at it. Fun running your code, exercising your code, seeing it work, confirming that you know what you're doing. Testing. So in conclusion, for all the doubters, automated testing, very, very important. More important even to new students, because you know, new students don't even know, they're not confident in their ability to write code and know that it's going to run and do what they expect it to do. Encourage new students to test from the get-go. It'll pay you huge dividends. It'll make you a better developer. It's what is done in industry. I guarantee you, you know, if you're on a NASA team, you're not writing code, deploying it on your Mars rover, blasting it off into space without having to have written 100% code coverage with automated tests that your code does what you expect it to do. I guarantee you. So, hey, if you're doing this with an eye and an idea of being in a career that does software development, this is the kind of stuff that you're going to have to do. And by the way, competitive teams, they're not competitive by accident. They have processes and methodologies and behaviors that they exhibit that cause them to perform well. Good software performance is achieved by valuable and repeatable testing. It's just a fact. And with that, good luck. I'm signing off. Thanks for watching.